Hey everyone, in the last video I left off saying that section 1 of chapter 17 deals with solutions that are mixtures of various components, which is unlike chapter 16 which deals with only solutions of just one component. So if I look at this particular solution that I have right here, if you guys can imagine, this is just a beaker that just contains water. You guys see how it's only one component that I'm tossing inside of the solution. So this is how generally problems in chapter 16 are phrased. You only have one component being tossed into water, and the question is, well, what's the pH of the solution? And I said, like I just said, chapter 17 is different because now you're dealing with solutions that are mixtures of various components. So the question is, now, what happens when you're dealing with solutions that have multiple components inside of them? And that's really the whole focus of this section of chapter 17, a common ion effect in acid-base equilibria. I have a solution that has multiple components. What's going on inside of that solution? What's the pH of the solution? How are reactions inside of the solutions being affected when you have multiple components inside of them? And that's really what this section is about. And it's an incredibly important section because when you move on to buffer solutions, you won't understand buffer solutions if you don't understand what happens when you mix multiple components inside of a solution. So please pay attention to what I'm going to do now for these couple of examples. And then in the next videos, we'll cover buffer solutions and titrations and etc. Okay, so like I said, the question that we're asking ourselves now is what happens when you mix more than one component in a solution? So what I'm going to do is I'm going to go through 3 quick examples just to show you what happens when you mix multiple things together. So let's look at this particular beaker right here. And we're going to call this beaker solution 1. And we're going to say that this right here is a mixture of 2 components. First component is a weak acid. And a strong acid. Again, notice that this is 2 components being tossed into the solution. I'm going to pick a very arbitrary weak acid, something like acetic acid. CH3COOH. And I'm going to pick an arbitrary strong acid, something like HCl. So again, I have a solution that's a mixture of 2 components. Notice that it's a weak acid and a strong acid in this case. Again, it's unlike chapter 16 because 16 only dealt with solutions that had 1 component. This now has 2 components going on inside the solution. So let's take this a little bit at a time, right? So imagine that I have this beaker. Now this beaker right here inside is filled with H2O liquid. H2O liquid. And again, these things aren't very hard to imagine in your head. Imagine you're home, you have a beaker, you place it on your counter, and you put water inside of it. And then let's say that you put in acetic acid into this beaker. What's the first thing that happens when you throw acetic acid in a beaker that only contains water? What reaction is going to occur? Well, we know that acetic acid is a weak acid, CH3COOH. We know that it's going to react with water, H2O, and it's going to come into equilibrium, and it's going to form CH3COO- plus H3O+. So we know this is the first thing that's going to happen. I throw acetic acid in water, both components are going to react with one another, CH3COOH and H2O. When you have an acid react with water, it's going to form its conjugate base and a hydronium ion. Make sense to everyone? So eventually what's going to happen is that this reaction is going to go to some sort of equilibrium. Now, just to denote equilibrium, I'm just going to draw a simple little scale, just to show you guys this. So, draw that. Here is the reactants, and here are the products. Like I said, all reactions, especially weak acids, those that go to equilibrium, are going to eventually reach some sort of equilibrium. And I'm going to denote equilibrium just by having these 2 little, imagining like a little scale in my head for now. Now imagine that this reaction has reached equilibrium. Now the question is now that we're asking ourselves is, what happens when I toss in a strong acid into this solution? Now let me recap just one more time what I did. I had a beaker that only contained water initially. I took acetic acid, I tossed it into the water. What happens when acetic acid comes in contact with water? Those 2 components are going to react with one another. You're going to form its conjugate base and a hydronium ion. Now we know this is a reaction that goes to equilibrium, and it's going to come to some sort of equilibrium at the end. And we'll just denote it by this little scale that I just drew, just for now. This is not to say that we have equal amounts of reactants and products. It's just to say that this reaction came to some sort of equilibrium. Now what happens when I toss in a strong acid into water? You guys know that strong acids, when they come in contact with water, completely dissociate. So the question is, how do I draw that reaction out? HCl plus H2O, when they react, it's going to form Cl minus plus H3O plus. Notice that hydrochloric acid completely dissociates when it's thrown in water. Look how it's denoted just by one straight arrow. It's not a reaction that goes back to equilibrium. This is a reaction that goes straight in the forward direction. Strong acids and strong bases completely dissociate when you toss them inside of water. Notice what's happening in this question. Notice what's happening when I toss in this strong acid. When I toss in the strong acid, I'm increasing the concentration of CO minus inside of the solution. But also notice that I'm also increasing the concentration of H3O plus. What happens if I increase the concentration of H3O plus into the solution? Do you guys see how acetic acid donated hydronium ions into the solution, and so did hydrochloric acid? Do you guys see how this is a common ion between these two reactions? Acetic acid produces hydronium ions, and hydrochloric acid also produces hydronium ions. But notice that when I added this hydrochloric acid, I increased the amount of H3O plus inside of this particular solution that I have. Notice that I increased the amount of products. Do you guys see how this reaction is now off balance? It's no longer at equilibrium. Now, if I ask you, which way does this reaction have to shift in order to go back to equilibrium? You guys learned in chapter 15 when we were going over the Chantelier's principles that this reaction would actually have to go from right to left. So it's actually going to go in the reverse direction. And notice, just for those of you who don't see it, what I always do is I always draw out a scale. I increase the amount of products, and the question is, how do I bring this equation back to equilibrium? I take some of the products and I place them on the reactant side. I'm going from right to left. I'm going in the reverse direction. And notice that in this case, I am suppressing the ionization of acetic acid. And this right here, and this is a prime example of what happens when you mix multiple components inside of a solution. Here in this case, I was working with a weak acid and a strong acid. Whenever I mix a weak acid and a strong acid, notice that I'm suppressing the ionization of that weak acid. This reaction gets shifted in the reverse direction. You guys, more importantly, what I want you guys to take away from this is which way reactions are shifting. In this case, this reaction is shifting toward the left. And why is it shifting toward the left? Because when I added this strong acid, that hydrochloric acid, the hydrochloric acid increased the amount of hydronium ions inside of this solution. And since the amount of hydronium ions were increased inside of the solution, that means that this value right here, that value increased. And how does this reaction compensate when the amount of H3O plus is increased inside of the solution? It has to consume some of that H3O plus, so it's going to go in the reverse direction. Make sense to everyone? Okay. So that's just solution 1. Now let's go on to solution 2. And let's say in this particular beaker, I mix something like a weak acid. Again, it's 2 components. A weak acid and its salt. Again, as a weak acid, I'm going to pick acetic acid, CH3COOH. And its salt is going to be sodium acetate. Sodium, CH3COO. Okay, again, same scenario. Let's imagine that I have a bucket that just contains H2O liquid, just contains water. Then I take some acetic acid and I toss it inside of the solution. Again, like we did over here, what happens when acetic acid comes in contact with water? We know that they're going to react with one another. So CH3COOH reacts with water plus H2O, and that's going to form its conjugate base, CH3COO minus plus H3O plus, correct? And again, this reaction is eventually going to reach some sort of equilibrium. Why? Because it's a kind of reaction that does not completely dissociate. It's one that reaches some sort of equilibrium. Again, I'll denote equilibrium just by drawing a scale with reactants and products, and just like that. And again, just to repeat this one more time, this is not to say that I have equal amounts of reactants and equal amounts of products. This is just to show you that this reaction is at some sort of equilibrium. What the exact amounts are, don't worry about them for now, but that does not mean that they have to be the same. They can be different amounts, and it could still be at equilibrium. But again, I only draw this scale out to show you that this reaction is one that goes to equilibrium. And how do I denote equilibrium? I just draw a simple scale with reactants and products. Okay, so that's what happened. I had a beaker that contained water, and I took its weak acid and I tossed it inside. Now, what happens when I toss the salt inside of the solution? Now we know that when you throw salt inside of water, we know that they're going to completely dissociate in this case. So if I look at something like sodium acetate, NaCH3COO, when I throw it inside of water, this is a strong electrolyte, by the way. Strong electrolytes meaning that they're going to completely break apart when you put them in water. This is going to form Na plus CH3COO minus. Notice what happened when I tossed the salt inside of this solution. What did I do to the solution? I increased the concentration of sodium plus, and I increased the concentration of CH3COO minus. Notice here, what happens to this reaction when I toss in this salt? You guys see how this right here is the common ion between these two reactions? CH3CO minus, CH3CO minus. This is the common ion between the reactions. And notice that what I'm doing is that I'm increasing the amount of CH3COO minus inside of this solution, meaning that I'm increasing the amount of products that I have. Again, if I increase the amount of products in a reaction, how is this reaction going to compensate for an increased amount of CH3COO minus? It's going to want to go in the reverse direction. It's going to want to go from right to left. And why? Because it wants to consume some of that acetate ion. It wants to get rid of it. And again, if you look at the scale, how do I bring the scale back to equilibrium? I got to take a little bit of the products and put them on the reactant side. Because again, I want a scale that is at equilibrium. So in this case, when I have acetic acid and I toss in its salt, the reaction is again going to go in the reverse direction. The reverse direction. And again, what's happening if I move this reaction in the reverse direction? I'm suppressing the ionization of CH3COOH.